Now let's use this figure to explain the case where the inputs to a function f as well as the output are vectors. What we see in the middle is the computational node that computes a function f. And as input, as before, we have one vector x and one vector y. Now, in contrast to before, x and y are vectors and not scalars. And in this notation here, we denote the dimension of the vector x as d subscript x. So therefore, the dimension of y then is dy, and the output vector z has dimension dz. Again, in the forward pass, the data travels along the direction of the green arrows. So x travels and is an input to this node f. And in the backward pass, the data travels in the backward direction along the direction of the red arrows. And so on the green arrow, again, we see the vector x, and then the corresponding red arrow, we have the derivative of the loss function with respect to the same vector x. So here we see z going in the green direction, and then derivative of the loss function with respect to z in the other direction. Looking at the data, we can observe that the data traveling in both directions has the same dimensionality. So z has dz dimensions, dz components, and the gradient also has dz components. The same is true for these other edges. We discussed that if we look at the derivative of a function f, then what we are interested, when we want to know how many components we have, this is a product of the number of inputs times the number of outputs. So the number of partial derivatives, the number of combinations we can form, would be dx plus dy, these would be the inputs, and then times dz, this would be the number of outputs. So that's how many partial derivatives we could form overall. However, looking at the derivatives, called Jacobian matrices here, they are split into two groups. One group that corresponds to this input x here, and the other group that corresponds to this input y. So we are actually going to form two derivative matrices. The first matrix that corresponds to x has the dimensionality dx times dz. Now, as observant follower of this class, you should be a bit suspicious about this dimensionality here that is used in the Stanford course. Why? Because the derivative matrix has as many rows as their outputs and as many columns as their inputs. So you see in this notation, the Jacobian matrix has actually been transposed. And therefore, these equations here, they actually have been transposed as well. The somehow advantage of this notation is that we have the matrix, the Jacobian matrix here first, multiplied with dl dz, which is a vector. So we have a traditional matrix times vector product here. If we evaluate the local gradients, or the local derivative dz dx, times the upstream gradient or the upstream derivative. Now, the more correct or the more consistent way would be to actually have these matrices be transposed, and then there would be, this would be a row vector that then would be multiplied from the left side with the matrix. But as you know, if we transpose a matrix vector product, then it's just, it's an alternate way to compute. You just get the transpose of the output. All right. So we can have the same if we look at y. Again, the downstream gradient now is the product of this Jacobian matrix, or the local gradient times the upstream gradient. Here we see a visualization of a ReLU functional block. So we have a function that computes the max of 0 and x. So for example, as input we have 1, minus 2, 3, minus 1, and then as output we would get 1, 0, 3, and 0. So computing the derivative, what is going to be the shape of the derivative? We have 4 inputs, 4 outputs. That means we have 4 times 4 partial derivatives. So the derivative matrix will be a 4 by 4 matrix written here. And this was an example we computed before. So you see on the diagonal, if there's a 1 or 0, is determined if the max was either clamped to 0 or if the max passed through the input value. So in the first and the third dimension, we passed the input value through, and in the second and fourth dimension, the value was clamped to 0. So let's say we have some upstream gradient here, and then this derivative matrix is just multiplied with this upstream gradient, and then we get the gradient that is dl dx, that would be the downstream gradient. So these values here, these are just set completely arbitrary. This is not derived by some computation. This is just an example of some upstream gradient that could come down during backpropagation. Let's also think about some possible data size for just such a ReLU function block. So maybe as input we have a tensor of size 512 times 512 times 64, so that's already on the larger side. Then how many partial derivatives would we have? Well, the number of inputs is the same as the number of outputs, and then we will realize that this Jacobian matrix is going to be really massive. However, it doesn't contain a lot of information. All the information is on the diagonal. But just with this one ReLU example in a more realistic setting, we can notice that forming these matrices, these derivative matrices, is actually not an option for the implementation. It would make everything very convenient and consistent, but we need a function that can compute this combination of the local derivative and the upstream derivative more efficiently. And so this is what happens in the code. So you will not see the code forming very large matrices that are sparse on top of that, and then compute matrix vector multiplications. Now, this would make everything like very consistent and compatible. It's just unfortunately not an option with the very large data sizes that we deal with. Here we look at an example of matrix backpropagation. And in order to avoid computing with tensors, this is an example that's somewhat simplified, where we are doing some unrolling of matrices in vectors. We just store the matrices as data traveling along the edges, but then for doing the computation, at least conceptually, we're going to unroll the matrices into vectors, and then the derivative higher order tensor will be unrolled into a matrix. So now X here is a matrix itself, and it has the dimension dx times mx. The corresponding derivative has the same number of components. It will also be dx times mx. This functional node now, this takes two matrices as input, one matrix X, one matrix Y, and it also has a matrix Z as output. We note again that the data that travels upstream and the data that travels downstream, the gradients, have the same dimensionality. So dz times mz for z and dz times mz for the gradient. The Jacobian matrices here are formed by, again, unrolling the matrices into vectors. So this matrix X would be a vector that has dx times mx components. And this matrix here would become a vector that has dz times mz components. And then this Jacobian matrix would have that many rows, dx times mx, and that many columns, dz times mz. As before, this is actually the transpose, but again, it's hard to keep this consistent, and they use again the transpose because they would like to have a matrix times vector multiplication for the computation. So if you are thinking about the Jacobian matrices or the derivative matrices, what we're thinking about is maybe how much does each entry in X, and we have dx times mx of these entries, how much does each of these influence each entry in Z? And so we have dz times mz of those. Therefore, we have to, therefore we're able to have this large number of partial derivatives because there are so many combinations. However, thinking of what comes back here, we're only thinking of how does each entry in the matrix X influence the final loss. And here we have a lot fewer combinations because there's only one single loss. So we only have one component for each component in X. Let us look at this example of matrix-matrix multiplication. As input to this computational node, we have two matrices, matrix X and matrix W. The sizes of the matrices, given in brackets, have to be compatible, so that the number of columns of the first matrix, D, has to be the same as the number of rows of the second matrix, W. And then the multiplication will give a matrix that has the size of n, the number of rows of the first matrix, times m, the number of columns of the second matrix. So we can observe that this is true. Y is n times m, and so we have a 2 times 4 matrix. Now we could ask, what are the local derivatives? For example, dy dx. The size is pretty big, and then notationally, do we want to write this as a matrix that is pretty big, or do we want to write it as a rank 4 tensor? It's going to be a bit tricky here. So one alternative, so we don't really need to write it down, is just thinking about for now, how does one element of this tensor / matrix look like? So the partial derivatives, they tell us how does, let's say, one input that is one of these 6 elements of X influence one output that is one of these 8 elements of y. So for example, we could ask, how does this particular input here, that is at where we have -3, how does this influence this particular output here, where we have a written 2? Now, if you do this matrix multiplication, then conceptually we could, for example, separate it into considering the rows of the output matrix Y. And what we then will observe is that the first row here of the output matrix Y is created by the first row of this matrix X, and the second row of Y is generated by the second row of X. Since we're interested in one element here in the first row, we can, for now, ignore the second row of X. So we'll just look at the first row. And then we have an inner product between a row of X and a column of W that gives us one particular value. For example, the inner product between the first row of X and the first column of W gives us this element -1. Let's just check that this is true. For 2 seconds, we have 2 times 3 plus 2 is 8 minus 9 is -1. Okay, this looks good. So this 2 is generated by taking the inner product between the first row and the third column. Okay, let's also very briefly check that this is true. So we have 2 plus 3 is 5, minus 3 is 2. Therefore, how much this -3 will influence this 2 here, so if it would slightly be perturbed, this depends on this entry 1 here at this position of the matrix W. Now, let's look at the final result. So if we want to propagate something downstream, we are interested in dl dx. Now here we have a lot fewer values. There are only 6 values here. So for every component of x, we ask, how much does it influence the loss function? You know, that's way further down in the graph maybe. And one important thing to take away, as we're going to skip over some detailed derivation, this is something you can do by yourself if you want to compute it at least once maybe. Let's just go to the output. And the output has to have a particular shape, and if the shapes are not symmetric, you know, if these are all different different numbers, so if n, d, and m are different, then how to compute that basically is immediately evident, because this is the only way how the shapes match up. This is how you compute. So on a high level, we know that from the product rule, having this simple scalar multiplication, how x changes the output depends on w, and how w changes the output depends on x. So the local gradient for x will be something involving w, so we'll keep w in mind for now, and the upstream gradient, upstream derivative, dl dy. So let's just find the way to multiply dl dy with w and hope to get out the same shape as this. And if we do this, then this should be the only way, there should be one way, and this will be the correct way. All right, so we want to have 2 rows as output, so we need to start with a matrix that has 2 rows. So we'll take this matrix dl dy. And then we want to have 3 columns as output. So can we just multiply this with w? No, this gives us a syntax error. So we have to take dl dy times W transpose. And then we obtain a matrix that has 2 rows and 3 columns. Now similarly, we could ask, what is DLDW? Now we would like as output a 3 times 4 matrix. So we will try to find a way to multiply DLDY with X such that we get a 3 times 4 matrix. And how can we do that? So first we need something with 3 rows. How can we get that? We take X transpose. And then we multiply X transpose with DLDY, and then we get a 3 times 4 matrix. On these slides there are some comments similar to what we discussed before, just written down explicitly. And here we have one more example that we'll also skip here. So here we want to discuss higher order derivatives. Here are 2 examples that by manipulating the ability to differentiate somewhat automatically in PyTorch, we can do all sorts of cool tricks. So for example, let's say we want to do something with second derivatives. The Hessian matrix is a matrix that collects second derivatives. So we have the second derivative with respect to the loss. So the input variables, how we look at x0, the input variables, and we have d2l, the x0 square. So this is the notation for the second derivatives. And the whole thing could be seen as a notation for the Hessian matrix. The input to the network is a vector here x0 that has dimension d0. That means that the second derivatives, the Hessian matrix, will have d0 times d0 entries, so it will be a d0 times d0 matrix. What we see here is a mini network that has 2 functions. So first x0 is input to this function f1 to compute x1, and then x1 is input to this function f2 to compute the loss that is scalar. We can make a transformation, but now this is going to be specific to one particular task. That is the task of multiplying the Hessian matrix with a vector v, and this vector v should not depend on x0. So this is going to be a matrix vector multiplication, and this is the dimension of the matrix, this is the dimension of the vector. All right, so to perform this particular task, we start with this network here, and we're going to add a derivative function, so that is f prime 2, so that means this function here computes the derivative of f2 explicitly, and we could just add it as a maybe node to the network, and then as output we obtain dl dx1. And then we could have another node in this computational graph that computes the derivative of function f1 explicitly, and as output we would get dl dx0. And after that, we could have a function added to this computational graph that computes the product, the dot product, with the vector v. And as output, again, we would get a scalar. So here we have a vector as output of size d0, inner product with v gives us a scalar. And the output of this complete network then will be dl dx0 inner product with v. And this works because we broke down the computation into 2 steps. First, we'll take the first derivative, which is going to be a vector, and the inner product with v, which is going to be a scalar, and then we take the next derivative. And then this is equivalent to taking the Hessian times the vector v. And we can do that by constructing this type of network and then backpropagating through it, and then this will be a way for us to get the product of the Hessian times the vector v. So this is maybe a bit more tricky in the details, but we're going to mention it here on a high level that these type of cool tricks are possible. Another such trick is the idea of a regularizer that was proposed in the context of generative adversarial networks. And this is the paper. You can click on the paper if you want to look at it. All right. So we want to have a regularizer on the network weights. And what we would like is, we would like that the gradient, and that means we have the squared L2 norm of the gradient, we would like that to be small. So that means, let's say we have a regular network, and then we would backpropagate to the network. Then we would like that the network tells us that the changes to the weights, the parameters of the network, are small. So the derivative of the loss function with respect to the network weights should be small. So this is just a fancy regularizer that could be used. Now, what is, how can we reformulate that? We can reformulate that as, so the squared L2 norm is the vector transpose multiplied with itself. All right, so what is the derivative of this term R of W? So what is the derivative of the regularizer? So since the term itself already has derivatives in it, the derivative of the regularizer we can note has second derivatives in it. And here again, we can kind of construct a more complicated network where we have these functions that are derivative functions, and then here we have a norm function instead of this dot product function from before. But this is now basically a function that takes the dot product of this output with itself, so we get a scalar, and then again we can backpropagate through this network to obtain the right solution. And again, maybe this requires some internet search and reading the paper to obtain more details. In general, I consider these, well, I don't know how exactly to call it, but let's say it advanced hacks or these possibilities that are enabled by automatic differentiation extremely exciting, and I think there can be many exciting applications of that and many exciting ways to apply that to different problems. Let's also add one more note on the memory consumption. We said in the forward pass we're going to evaluate the graph and store intermediate results. And this is memory consuming as this scales linearly with the batch size and the number of layers. So the more layers we have, the more intermediate results, and the more samples we consider in the batch size, the more intermediate results we have. In the backward pass, we evaluate the graph in reverse order, as we said, and we do have some possibilities to evaluate paths that are not needed. Generally, during training, maybe we don't need to evaluate the derivatives with respect to the input samples. Still, memory is a big issue. We will see for some of the more memory-consuming networks, for example, segmentation, it might be 1, 2 samples, that's all that fits in your GPU memory. there's the concept of rematerialization that says we can actually trade off computation for memory. For example, we can compute things twice and save memory. So the ReLU computation, for example, would be very cheap to recompute. Maybe we don't want to store the input and the output of a ReLU as intermediate values. For convenience, then the memory might not be the memory consumption might not be worth it. Maybe a conv layer, this could be more expensive. Then here we want to be maybe careful if we want to throw it away or not. But in general, there's this principle that you can throw away intermediate computations to save memory and recompute them. So we'll look at this figure here. What we see way on the left is the visualization of, first we have the forward pass, so we go through the graph bottom up, so this is the end, so here we have the output, and then we have the backward path, and then in the backward path we kind of always consider the data flow, but we always need to fetch the intermediate information from some of the nodes in the forward path. So where exactly this is stored, if this comes from this node here, from this node there, this is like some detail we'll skip over, but pretty much every node here you need to kind of fetch some information from the forward path. So what we could do is we could split the network into multiple parts. For illustration purposes, we take two parts. So we have this first part here and the second part here, and then we only store the intermediate results at the head node in each part. Then, during runtime, what we can do is when we are doing backpropagation here, we're actually not fetching pre-computed values from these nodes here. We would have to engage in recomputation. So we have to recompute the forward path here and then use the values from the recomputation. And in this way, we are actually saving the storage, saving the memory for storing intermediate values for this node here and this node here, because these would be recomputed. Starting from this node here, this is the one that has been stored. And then for the first part, we are this figure here, we would, again, we only have this value here stored. So if we rely on intermediate values from this node or this node, we would have to recompute them during the backward path. That means during the backward pass. Okay, this concludes the lecture on backpropagation.